Welcome back, everybody, and today we're going to finish up with experimental research as we take a look at validity, both internal and external. How do you know that your research design is really measuring what it's supposed to measure? Well, there are ways that we can check that. Now, we're also going to be taking a look at some formulas in statistics that we're going to be using not just now, but in the future. So let's go ahead and get started as we finish out this chapter in experimental research. Okay, everybody, let's finish up with experimental research as we start taking a look now at internal and external validity. Internal validity, as you see here, is the extent that a variable, experimental variable, is truly responsible for any variance in the dependent variable. In other words, does the experiment, is it designed the way it's supposed to be designed so that you get an accurate result? For instance, as you see here, does the experimental manipulation truly cause changes in the specific outcome of interest? If you remember last week when I told you about the experimentation at the Hawthorne, Pennsylvania GE plant, they started turning down the lights just a little bit imperceptibly over a long period of time, and they were wanting to look at how the workers would respond to those adverse conditions. Well, if they applied the same methodology, the same manipulation to maybe the second and third shift, and they saw the outcomes about the same, then you would have internal validity. That means it's measuring the manipulation is measuring what it's supposed to measure or having the effect that it's supposed to have. Manipulation checks, again, this is, we can use this same example where you check it out. Instead of just looking at one group, you would look at several and manipulating the dependent variable in the same way, you would be able to make sure that the research or the test is valid. History effect. This occurs when some change other than the experimental treatment occurs during the course of an experiment that affects the dependent variable. For instance, the book talks about you dividing up some managers, and you're looking at the independent variable, which may be pay and benefits. The dependent variable would be performance. And the first group could be acting in such a way when the company advertises, we're going to give you pay and benefits, but let's say that something happened economically and the incentives had to change, so that would affect the rest of the groups who had not been told how their pay and incentives would be changed. So there may be a difference in how they behave and the way that the others had behaved who had been given the favorable types of benefits and pay and so forth. So it would have been the historical event that happened. You may come and take a test, and the test may be a pre-test on, let's say, or an exam on, let's say, business. And you might have had some event take place. Let's say, for instance, you might have had a tragedy in your family, and then you come to take the test again, and you don't do as well because your mind is maybe stuck on a family crisis or whatever. That could be, in a way, a history effect as well. The cohort effect is a change in the dependent variable that occurs because members of one experimental group experience different historical situations than members of other experimental groups. And that would also be an example that we just used with the managers and pay. One group could be influenced and then something could happen in between you measuring cohorts, and because of the event in history or in time, that influence could have an effect on the second cohort group, so that would render your experiment really invalid because of the effect of the event or the time span that transpired between you being able to really check one group against the other. Maturation effects, and these are changes that take place in time that will alter your experiment. For instance, you may have a individual or individuals that you're experimenting with, and as they grow older, they may change and you may get different results. For instance, you may see their exercise habits changing as they grow over, maybe 5 or 10 years down the line. So you're going to have that as well. Testing effects, and this is just, the test is not designed in a way where, well, not the design itself, but let's say you test somebody and you test them again, they're going to be aware or sensitive to maybe things they discovered in the first test, which would alter the way they responded on the second test. For instance, when I was in the military, we used to use a military entrance exam called the ASVAB, and oftentimes they would take the test the first time and not do very well on it. But when they went back and maybe studied a little bit more, or they kind of understood the way the questions were worded, they were better prepared to take the test the next time. So that can affect the validity of the test. Instrumentation effect is a change in the wording of questions or a change in interviewers or anything that can change the respondents or the dependent variable through those changes. I may ask interview questions and get one response, and you may have someone who is more easygoing or someone who is more rigid, and the outcome may be quite different. Selection, again, this is sample bias, where we have selection error. It's not really a random sample, but we have contaminated the selection process. Mortality effect, which is just attrition. People withdraw from the experiment, and the longer these experiments go out as far as time length, the more likely that's going to happen. External validity deals with the ability for the test to accurately represent real life outside the experimental realm. If I tested, let's say for instance, students' aptitude to be able to go to college, and those tests accurately predicted performance in universities and in trade schools or whatever, then that would be an external test that has validity in it. Workers, if I experimented with workers and their abilities, and they were able to transfer that into the workplace, then it has external validity. Trade-offs between internal and external validity, they show you here that laboratories usually are high in internal validity because you can control that more, but the external validity, that has more bearing on field experiments and where you see people in their natural habitat. Now, when we design experiments, we want to be able to do several things. And you see here some formulas that the authors have provided us. One is the basic experimental design, where you have one treatment, you have one independent variable and one dependent variable. So X would be a representation of the treatment itself, the experimental treatment, which would be the independent variable. Observation would be the dependent variable. And if you're making more than one observation, you see here you have O1, O2, and on and on. Now, R within the square represents that there is a random selection of these respondents or test units that you're going to be using. Now let's talk about quasi-experimental designs. These are experimental designs that do not involve random allocation of subjects, so you don't see the R there. They're not randomly selected. Rather, they are selected based on the nature of the test. So you have a one-shot design. You have the experimental treatment, and then you have the dependent variable, the effect of it in O1, or the observation of what happens when you integrate the experimental treatment. You have one group pre-test and post-test. You observe behaviors with a pre-test, then you introduce an experimental treatment, which may be education on something, and then you test them again and observe it. That's O2. You have the static group design, where you have an experimental condition. You introduce X, which is maybe the training and education, and then you test a person or the group. That would be O1. And then you have a control group. They've been given no experimental treatment, which means they've been given no education, if that's the independent variable that you're going to have. And then you would see the observation, and that would be the dependent variable of that group, and the results would be O2. Now this is pretty much the same. The only thing you're doing is introducing now a random sample. So you see again the pre-test, post-test. There's nothing really going on here other than you have an experimental group that was randomly sampled. You have the pre-test and the experimental treatment, which is the training, and then you test them after the training. That's the experimental group. The control group, you have the same thing. You have a random sample, and you have the pre, and then the treatment, and then the post assessment. And then you have here post-test only control group. So you have here the experimental group with the random sample. You give the treatment, which is X, which may be the training and education, and you look at the outcome. The control group would not receive any training. So up at the top, you're comparing groups. Down at the bottom, you are withholding treatment. You're still comparing, but you're withholding the experimental treatment in the control group and seeing how well each group performs. Completely randomized designs, that just means that you randomly process, or it's a random process to assign subjects to treatment levels, and the book talks about some ways of doing that. You can use a computer, let's say, to identify some people, and then once a few of them have been identified, then you can take the rest. Every third person after this number, or every fourth person, or whatever, will get a number, and that would assign them to one group or the other groups, or whatever, as the random allocation exists. But the key here is you want randomization. You want to make sure that your selection process is not biased in any way, and that what you use to select the people is unbiased. Now, you see here there are some longitudinal, and that's over time. When you take a look at time series outcomes, you're taking a look at how changes occur over time, and the upper left hand, you see permanent change. So you have 0.1, which is between 1 and, let's say, 3. At the 3.5 mark, you see an experiment, the experimental treatment. And then from 4 to 6, you see an increase and then it leveling off. Temporary change, you see from 1 to 3, how things are before the treatment. Between 3 and 4, you see the treatment. But then you see an increase all the way to 5, and then it drops off. Perhaps people received training and they were good, but they forgot their training. And that's called extinction. And then you see the drastic drop-off of the change. No change you see here at the bottom left. It's just a straight line across. And then continuation of trend, the lower right hand, you're going continually up. So you are steadily increasing the observation or the dependent variable, but that was already occurring before the experiment was given or the treatment was given. So you might have to wonder, did the experimental treatment perpetuate the growth, or what happened here, or did it really have an influence, because you see a continual growth either way. Well, today we took a look at the importance of validity to make sure that your research is going to be above board and that it's going to measure what it's supposed to be measuring or assess what it's supposed to be assessing. You've got to maintain that. We also took a look at some basic research experimental designs, so that'll give us enough to jump into the subsequent chapters that will deal a little bit more in research formulas and designs. Hope you have a good day, and we'll see you tomorrow.